Been a while since I was here, so I thought, you know what? I want to check with my own two eyeballs, give it the chew test. So this is why it's important to get up and get your nose up against the outcrop after you first look at it from afar. Lots of little marine trace fossils squigging along the surface, probably among the most controversial in the world. Very high energy, whack, very low energy. That went over like a lead balloon. A phrase that's come under a lot of scrutiny recently for all sorts of reasons is the science is settled. Now that's something that you hear from a lot of researchers when they simply don't want to discuss a topic anymore, or they actually believe that there's nothing more to learn about it because we already understand it completely. Geologists being scientists are just as guilty as anybody of this, and if you've ever been on a field trip either as part of an academic group or an industry group, or just an interested party looking at some rocks, you've probably heard the interpretation from the tour guide as to how these rocks got to be the way they are. With that in mind, I'm visiting one of the most famous and controversial outcrops in the world. It's in the Book Cliffs of Utah, just north of the little town of Green River and east of the Green River itself, and we're going into a canyon called Tusher Canyon. We're there to look at a river channel deposit, but it's not just any river channel. It was deposited in the Cretaceous about 75 million years ago. That much everybody agrees on, but where things fall apart is in the discussion of what kind of river did these deposits accumulate in. There's two main theories, and that's what we're going to be trying to evaluate today. The first theory is that this represents an incised valley fill, meaning that relative sea level fell during the Cretaceous, causing rivers to elongate and cut into older deposits before getting backfilled as sea level rose again. If that's the case, then by definition, the valley is surrounded by an unconformity or a sequence boundary. The second interpretation is that this is a simple single distributary channel fill, in which case there's no unconformity, no sequence boundary, and sea level did not have to fall. In fact, sea level might have stayed the same or even risen slightly as this channel prograded into its older deposits. Each interpretation is backed by really smart and really passionate geoscientists who differ in opinion, but are ready to fight it out at a moment's notice. You know, as we're driving in, it's always a good time to kind of start talking about the context, because I always tell everybody context is everything when you're talking about sedimentary geology. So for context, the rocks we're looking at here out the window are all part of what's called the Mesa Verde group. And that's a big succession of mud, silt, sand, and coals that accumulated on the western shoreline of the Cretaceous Western Interior Seaway. The seaway existed because the continental crust was actually sagging down into the mantle as a result of the severe mountains being thrust up to the west and putting a tectonic load on the continent. This allowed the Arctic Ocean and the Gulf of Mexico to flood the continent and meet up in what's called an epicontinental seaway or an epiric seaway, and we call it the Cretaceous Western Interior Seaway. It's important to remember that the Cretaceous was what's called a greenhouse environment. So while tectonics and climate had a major role in relative sea level and shoreline position, glaciation probably was not anywhere near as significant as it is in today's world. So that's enough context for now. Let's take a look at the rocks right outside the window. These are sandstone bodies that represent shore face deposits. They are deltaic shore faces, meaning these are the subaqueous or submarine parts of a delta that were affected by storm waves and to some extent tides. These marine deposits are grouped together as the grassy member, and overlying them is what we're here to see, which is the desert member, a fluvial section that incises the grassy, and that's what all the debate and confusion is about. And we're just now starting to see it through the windshield. In fact, you can see the incision in the channel right there.
Okay, now we're talking. So that is all fluvial. We're going to see if it incises. Creates a sequence boundary, unconformity, incised valley. Look at that.
Coming up around the corner here off on the left, you can just start to see the object of our attention, and you can get the impression of a big scour that's filled in with some flaggy heterolithic sandstone, and it's cut into a blockier set of sands. Those blockier sands are parasequences, or shore faces. Each shore face is called a parasequence. And a general rule of thumb is that if a fluvial section cuts into two or more parasequences, it's an incised valley. The word controversial gets thrown around a lot, especially in videos like this one. But in this case, it's totally warranted because right behind me, is a fluvial channel system with a scour that is probably among the most controversial in the world in terms of identifying sequence boundaries, unconformities, and what exactly that fluvial channel system is doing in relation to the underlying marine shore face deposit. Now, I first visited this outcrop sometime in the mid to late 1990s as a grad student, and the idea was pretty well established that that is a sequence boundary. There was a fall in sea level, there was incision, and that might even be a valley. Flash forward to when I was working here in the 2000s, when I worked in the energy industry, and I led many field trips here, and we began to question that interpretation and say, what is the actual evidence for there being a sequence boundary? That was always a fun exercise on field trips with geos and drillers and engineers and so on. Then a few years ago, Simon Pattison, a professor who's worked out here for decades, finally put to print what a lot of us were kind of scratching our heads and thinking about, and suggested there is no sequence boundary. There's no unconformity. This is a normal succession. That went over like a lead balloon with some people. A lot of people embraced it, and a lot of people, old school folks, have not. There's been back and forth on social media, kind of rumblings and interpretations and discussions at various conferences and whatnot. It's been a while since I was here, so I thought, you know what? I want to check with my own two eyeballs, because that's why I'm here today, and that's why you're coming with me. We're going to go take a look at that surface, the deposits above it, the deposits below it, and see if we can come to some conclusions about whether or not it is a sequence boundary or just a regular plain old fluvial incision surface. All right, let's take a look at those rocks. That's where the answer is. If it's a sequence boundary, that means that the fluvial section above should be cutting into shore face deposits, specifically lower shore faces below storm wave base. So we're going to start off in this corner and take a look at those lower deposits, see if that's something out of the ordinary, and check that surface above them, and work our way across and finally check out the big channel. We're going to see what exactly is going on with these rocks. So here's that lowermost succession. It's kind of in the shade here, but the good news is around the corner, it's in the sun. So we can get a good look at it. See what kind of sedimentary structures or trace fossils are in it. It's pretty heavily weathered, but it looks like there's hummocky stratification here. Hummocky cross stratification, HCS. And hummocky cross stratification, of course, is a fairly contentious topic of discussion among sedimentary geologists. Maybe I'll do a whole video on hummocks alone just to kind of capture some of that. But this sure as shooting looks like hummocky cross stratification. It's not crystal clear. There's a lot of this kind of surface pecking and weathering. But you can see those low angle anticlinal surfaces in here, typical of hummocky cross stratification. Take a look at these. Come down like that. And then they kind of seem to come back up a little bit. Anti-dunes, or sorry, anti-forms. So this looks fairly hummocky. Up there, same thing. You can kind of convince yourself you're seeing hummocks and swales. So, okay. So far, so good. But look at this. In amongst the hummocks and swales, we're starting to see some cross-bedding. Low angle, but it's there. And working our way up through the succession, you see some zones that have an increased amount of fine-grained material. That's manifesting as these kind of more recessive zones. So you've got sand-rich intervals, and they kind of are pinching out and swelling and pinching. That's that hummocky cross stratification, giving it that characteristic. But then the recessive units are the more quiet intervals. So we've got the sandy tempestites, tempest in a teapot, right? Or tempest in a teacup. So there's the storm deposit, and that's kind of more quiet, fair weather deposit. Then another storm deposit, and another quiet water deposit. So we're seeing episodic depositional episodes. And there's another one of these recessive units. The underside has some dimpling on the sandbite. They may or may not be trace fossils. Those might be things like Bergaria, or yeah, sure enough, it looks like there's some little surface trails, as well as flute casts, tool marks. But there's definitely some burrows. Like, look at that one. There's a thalassinoides, or probably a paleophycus. Looks like paleophycus. Some bivalve traces. So this was a storm sand deposited on a fair weather succession. Typical of a shore face deposit. Wave-dominated deltaic shore face, as so many of them are here in the Brook Cliffs. Yeah, look at that. There's some nice larger burrows. That's a pretty good size one. Unfortunately, some people have left graffiti on the outcrop. Why you would do this, I don't know. But there it is anyway. But again, typical shore face succession or wave-dominated delta front succession. Ooh, look at that. You can even see some nice kind of hummocky or just undulatory beds. All right. Now we've got this big blocky sand to contend with. What do we make of this? All right, so this lowermost succession of sand, which is very fine-grained, it doesn't look like there's too much in the way of burrowing either, but it's got hummocky cross-stratification, swaley cross-stratification, and even the start of some cross-bedding. So that's indicating, to me at least, that we're somewhere above, obviously, storm wave base. We're getting some pretty good-sized hummocks in here, but we're not quite at fair weather wave base. So we're in the western interior. That can correlate to around, let's say, 15 meters of water depth, 20 meters of water depth, somewhere in there. It's variable. I understand. I totally get that, but let's just say 15 meters of water depth, give or take. So we're going to work our way up through the rest of the succession, up to the surface, see if anything changes. Because right now we're at about 40, 45 feet of water depth. We'll see if things shallow up gradually or if there's an abrupt truncation by a fluvial channel. That will be interesting. Here's a surface block from somewhere above. As you can see, it's got a variety of little trace fossils on it. It's got some meniscate backfilled structures like this. This might be tenedium, made by little polychaete worms moving across the surface, or possibly bivalves or something like that, or gastropods. So the big blocky sand has a fairly sharp surface where it contacts those lower to middle shore face deposits. Seems to scour down here. And then, unfortunately, it's hidden. But it looks like it does some more scouring over that way. So we're going to look in the sand, see if there's anything in it that gives us a clue. Looks like from fairly good-sized crossbeds. They're a little bit hard to see, but they're here. And they're giving an overall sort of east to southeast direction, it looks like. That's kind of low angle bedding. We've got some low scours here, little internal scours, and what kind of looks like, almost looks hummocky in here. But the surface weathering is just really making it challenging. But take a look at this. Let's examine that. Okay, so in the light, it's a lot easier to see some of these surfaces, some of the laminations, including right in here. And lo and behold, there's some very low angle bedding that could be hummocky. This sure as shooting looks hummocky. So swale truncated by hummocks. Hummocks and swales go together, of course. These are the depositional surfaces on top of this blocky material. And these chunks have fallen down, probably from right there. And they give us a nice view of what the surface actually looks like. And you can see the surface is sort of rippled. There's some texture to it that gives you the sense that it was maybe some lingoid ripples or tiny little hummocks or something. But more importantly, look at the trace fossils on it. So there's all kinds of surface traces made by little amphipods that made things like that gyrocorte, made by things, probably little polychaete worms and gastropods and little creepy crawlies like that, making their way across the surface, leaving these trails that were then preserved when the next bunch of sediment came washing in. Not much in the way of deep dwelling things, so not any ophiomorpha that I've seen anyway, or Roselia, or creatures like that, the shrimp and worms that made them. Instead, it's surface traces. Okay, so this is why it's important to get up and get your nose up against the outcrop after you first look at it from afar, because this first massive sand that you might think, well, that's a candidate for a fluvial system, big blocky sand, kind of scoured. In fact, it's chock full of hummocky and swaley cross-stratification with lots of little marine trace fossils squigging along the surface after the storm deposit happened. So this is pretty typical of an amalgamated middle shore face, middle to upper shore face transition maybe, but we're still, in considerable water depth to have this amount of hummocky cross-stratification. So we're still looking at maybe 10 meters of water depth, maybe a little less. Let's say about 30 feet, give or take. We're going to keep working our way around the corner here because that's where things start to get pretty interesting. Okay, so before we go charging up to the outcrop, let me just remind you, this big blocky section of rock behind me is one we were just looking at that's chock full of hummocks and swales and marine trace fossils on the surface. We're going to follow it across, and then, that's where something happens, because if I keep going across, even accounting for the dip, look at that. That's where my big channel feature is. So we're going to work our way across it, see what's happening at that surface and in the channel. So the hummocky, massive looking, but as it turns out not massive, hummocky and swaley sandstone is still here. Look at this, you can still see some faint indications of lamination. In a core, this would show up really nicely probably. So from afar, it looks massive. And that's a real key learning here, is things that look massive may not really be. And here we go. Here's that transition. So massive and hummocky gives way abruptly at a really sharp surface to that flaggy heterolithic material we'll take a closer look at here in a second, which continues on that way, and then the big scour comes through and appears to take out all of this. So this material is going to be key to putting together our story. What have we here? This is actually a silty, very fine-grained sandstone. Looks like mud, but it's actually not. And, I've showed you in other videos that the best way to actually test whether something's mud or silt or sand is to take it and give it the chew test. If it's creamy, it's a clay, mud. If it's gritty-ish, kind of gritty and creamy, it's got silt in it. And if it's really grindy, it's sand. This stuff is actually kind of a very silty mud. Then these little sands of a light color material. So we've got silty mud, sand, silty mud, sand. So very low energy compared to this very active middle to upper shore face down here. Let's call it upper middle shore face. So very high energy, whack, very low energy, and heterolithic. Energy levels going on and off, on and off. I've mentioned before how sometimes you have to step away from the outcrop to get the big picture. Your nose is right up on it. It might be hard to tell what you're looking at. So I was just looking at that transition between the massive shore face and the heterolithic material. And that seems to go across, and then there's the big channel scour. So what I'm going to do is continue to look at that heterolithic material and then pay particular attention to the channel, because it's actually cutting down through the heterolithics and into that upper shore face, that middle upper shore face, upper middle shore face. So that's telling us something. So let's get back up there and get a closer look. All right, so we're back to looking up here. And, this stuff, it looks like somebody was doing some sampling, or maybe it's just kind of eroding. But this material has what looks like some wavy and lenticular bedding. By lenticular, I just mean you kind of get these little lenses of sand. This is typical in tidal environments, or any environment where you get sort of, fluctuating energy. It can happen in little ephemeral streams and whatnot. There's some interesting relationships in there. This seems to be a sand that's come through and scoured out some of this material in a lozenge shape. So what is going on with it It looks concretionary, so part of what we're seeing might be an artifact of concretion, but it really does look like it's scouring out over there. Could be just a little scour trough that happens in some of these systems in a, if we go with this being maybe a lagoonal or back barrier system. Here's the shore face, middle shore face. Think of Galveston Island. This is the beach, off the beach of Galveston. This is where people go swimming. Maybe that's back barrier. This might be behind in the lagoon. Or this might be the toe of another deltaic system. So there might have been a flooding event, transgression. That's an interesting possibility. So we had a progradation, transgression, start of another progradation, and then whack, here comes our big fluvial incision. And it looks like there's some carbonaceous material at the base of that channel. So kind of going with the progradation idea, sure enough, it starts off very fine and thin and flaggy and starts to get more massive up there. You can see some low angle cross stratification, paleocurrents going roughly to the south. Interesting. Don't look hummocky though. It doesn't look like a shore face. So we're dealing with something different up here. All right, so now we're at the million-dollar question. What is the nature of that fluvial incision surface? Just to recap what we've seen so far, that lowermost part of the succession has features most consistent with probably a wave-dominated deltaic shore face. There's not much in the way of vertical burrows, suggesting it's a very high energy or freshwater stress system, typical of wave-dominated deltas, something like the Brazos River Delta or, one of those features. Then we have some sort of truncation surface at the top of that upper middle shore face, and there's the heterolithic radial material that, just based on this outcrop alone, we can interpret a couple of different ways. It might be a back barrier system that's stressed, it might be a lagoon, or it might be the toe of another delta coming on top. So in either case, you've got some sort of truncation and transgression in the case of if it's a delta prograding on top. In the case of a lagoon, it might be associated with possibly a fall in sea level. On top of that lagoon, we've got that channel scour, and that channel scour cuts through the lagoon, but also through our upper shore face. So that's telling us that something different is happening here. This is not a regular progradational cycle. Now the answer to what this fluvial channel is actually in the channel body. So let's take a look at it. And here's a close-up of that surface, cutting down and whack, there it hits that shore face. Cuts down, down, down into the shore face. Keeps going. Okay. So as always, before diving into the up close and personal touchy-feely, we're going to take a step back and see what we can see in this channel fill. It doesn't look like a typical fluvial channel at first glance, but it's got features consistent with one. So it's got, for example, sort of high angle bed forms that might be components of a bar, but it also seems to have a lot of organic material in it, a lot of dark, maybe coaly. From back here we're saying it's coaly, but we'll take a look up close and see. So it's not a typical coarse-grained fluvial channel. It seems more heterolithic than that, and it's got more kind of undulatory and laminated bedding than you would expect in a typical fluvial system. So that's something to keep an eye on. Let's take a look up close. So here are those intervals with what looks like carbonaceous material, coaly to carbonaceous material. And that's very, very low energy, sitting on top of sand, which was deposited during a big, river flooding event. But what's striking about them is there's not much in the way of burrowing. There's maybe a couple of little planolites type burrows, but they're not churned up. If this was an estuary or a really marine-influenced brackish water channel, I would expect to see a fair amount of burrowing in this fine-grained material. And I'm just not seeing that. So that's possibly suggesting there's a lot of fresh water. Here's our friends, the lenticular bedding again, which, it's consistent with tidal influence. Like I said, it's also consistent with a variety of other depositional environments, but tidal influence is certainly one way. That fluctuating energy is one way of creating that. Here's some really nice exposure of that heterolithic carbonaceous rich material. So a lot of plant matter, and that's typical of coastal distributary channels like the Trinity River down where it intersects the Trinity Gulf, the Trinity Bay. And there's some cross bedding, so dunes migrating west to east in a normal flood event, which is pretty much what you expect here with the paleo shorelines. Let's take a look further down. This is the base of the channel. The scour comes through right here, and it's debatable exactly which surface it is. It looks to me like it's actually this one here. And there's some foresets going in that direction. They've got what looks like maybe a little rip up clasts of sand. No, maybe not. That's just weathering. And there's another surface that comes through with some more material. And on the underside, aha, look at all this. We've got plant debris. So we've got a lot of organic material from the terrestrial realm. Plant stems. That's good to see. Oh yeah, rip up clasts. There they are. Pretty much what you expect at the base of a channel. Coarser grain material, plant stems. All right. So we do have rip up clasts of silt. Yeah, you can see them in there. There's plant material, exactly what you'd expect in one of these coastal fluvial channel bodies at the base where all the junk kind of accumulates. And there are even some pretty good sized clasts in the base of the channel. Look at that one. That's about maybe almost 25, 30 centimeters lengthwise. So good chunks of ripped up bank material in the bottom, along with a lot of plant material. So yeah, each of these flood events within the channel brought with it all kinds of stuff that washed in off the coastal plain. Mind you, that's sitting in a channel that's cut down into the shore face. Okay, I think at this point we have enough to kind of make some preliminary interpretations based on solid observations. Solid observation number one, this channel feature cuts through a previously existing deltaic or back barrier system and into an upper middle shore face deposit. That's visible right here. I just showed you that. Interpretation from that, there's a couple of them. Number one, this could be a subaqueous channel that's cut down off the delta and cut into the delta underwater. It's not a fluvial channel. It's a subaqueous channel that's scoured through, and that happens sometimes, and is then filling up with all this heterolithic material. The counter to that is, if that's true, why are the storms that are creating the hummocks in the shore face not influencing the channel fill? Even after a flood event, you would expect that to get reworked by storm deposits or fair weather. And certainly all the organic material should be washed out of there. It should be winnowed away. So that's probably not very likely. Interpretation number two is that sea level fell and that shore face below was truncated. And as the shoreline retreated into the basin, the fluvial channels extended behind it. And as they extended to keep up with sea level falling, they incised into the shore face. That was the going interpretation throughout the years of the 80s, 90s, and into the 2000s. Third possibility is that this is just a regular fluvial channel that has cut through after progradation of the shore face out into the basin, fairly straight trajectory, and it's cut down into pre-existing deposits as the entire system migrated horizontally out into the basin with very little change in sea level at all. Now, modern coastal rivers like the Brazos, Trinity, and Colorado on the Texas Gulf Coast have no problem cutting into their older deltas as shore faces. And the resulting pattern would look a lot like what we're seeing here, with fluvial deposits cut into hummocky, swaley, and lenticular bedding. But this one is cutting into two shore faces, not just one. So to me, that suggests there's something different going on here. It is not just a simple case of a single river channel cutting into its own delta front. It's a river channel that's actually cutting into two older delta fronts with who knows how much time missing, because we just don't have the chronostratigraphic resolution. In other words, we actually don't know how much time is missing between these deposits. So what could have caused sea level to fall in the greenhouse world of the Cretaceous? Well, the first possibility is tectonics, and any slight uplift in the basin would have had a net result of a relative fall in sea level with associated fluvial incision. Likewise, climatic cooling would have caused surface seawater to contract, and the result would have been a sea level fall. All right, so what is the verdict? Well, in the 80s and 90s, it was popular to point to this and say there's an anomalous incision surface, it's a sequence boundary and unconformity, and we've got estuarine or fluvial deposits sitting within a shore face. By the 2000s, it became vogue and popular to say, I don't believe that paradigm, I'm going to challenge it, and I'm going to say it's an autocyclic surface. In other words, just a regular old fluvial channel that's cut in after everything's prograded. After spending some time looking at this, you know, I'm sort of torn, but I think I'm going to have to come back to the original 80s and 90s interpretation of this thing, because the fact that we've got a heterolithic distributary channel cut through two successions of shore faces, that just seems excessive, and more importantly, it fits the definition of a sequence boundary and an unconformity, in that we've got proximal deposits sitting anomalously on top of more distal deposits with missing interval in between. In this case, we've got distributary fluvial system cut into two middle shore faces. Take it for what it's worth. There's 15 other interpretations out there. You could probably find them with a quick Google search or on YouTube. That's what I'm taking away from this outcrop though, and I got a lot of other stuff to see today. So as always, thank you for watching. I will see you on the outcrop, and take care.